In January 1700, a tsunami struck the coast of Japan. Waves rolled into harbors, swamped rice paddies, flooded homes. Japanese officials did what Japanese officials did. They wrote it down. The date, the wave heights, the damage, all of it recorded with the kind of bureaucratic precision that makes historians grateful 3 centuries later. There was just one problem. There was no earthquake. Not in Japan. Not anywhere their instruments or their senses could detect. A tsunami without an earthquake is like a shadow with no object casting it. Physically, it makes no sense, unless the quake happens somewhere so far away, so completely beyond the edge of the known world, that no one who felt the ground move had ever put a word of it on paper. The Japanese knew the ocean had risen. They had no idea why, and for nearly 300 years, neither did anyone else. But the answer was out there. It had been out there the whole time. Carved into standing forests, written into the rings of dead trees, and spoken aloud, generation after generation, by people whose accounts no one had thought to take seriously. The answer had been spoken aloud for generations. Not written, spoken, passed from elder to grandchild, repeated at winter gatherings, encoded in the kind of careful, deliberate language that a society uses when it needs something to survive. The huu-ay-aht people of Vancouver Island describe a night when the earth shook violently, and the sea rose and swallowed their village at Pachena Bay. The account is specific. It happened at night, without warning, and no one from that village survived. The Maka, whose territory sits at the northwestern tip of Washington's Olympic Peninsula, carry similar accounts. The ground moving, the ocean rising, the coastline transformed in a single night. The Quileute describe waves that reached places the sea had never reached before. For 2 centuries, researchers heard these stories and filed them under mythology. The professional habit of the time was to sort indigenous oral tradition into 2 bins, historical record or legend. These got the second bin, but details kept snagging. Several accounts describe something striking: the sea pulling back first, the water draining from the shore before the wave returned. That detail is not dramatic embellishment. That is physically accurate. A distant source tsunami, one generated far offshore, produces exactly that signature. The ocean retreats before it surges. A local earthquake produces a different pattern entirely. Someone describing that withdrawal had seen it happen, which forces a question no one had seriously asked yet. Could an oral tradition passed down for 300 years actually preserve a reliable description of a geological event? The answer is yes. But that answer immediately raises a harder problem. If the oral accounts are describing something real and the physics says they are, then researchers needed independent confirmation, a way to test the tradition against something that wasn't itself a tradition. And in 1700, the Pacific Northwest coast had exactly one class of potential witness: the people who lived there. No European had yet built a permanent settlement north of California. Spanish ships had sailed the outer coast in the years before, charting headlands, naming capes, but none were anchored in those waters that January night. The absence of any European record isn't a gap in the evidence. It's a fact about when this happened, before the coast was colonized, before anyone carried a logbook to those shores. The silence in the archives is precisely what you'd expect, but that creates a genuine methodological wall. Oral accounts can carry physical detail across centuries, as the sea withdrawal descriptions show. They cannot, by themselves, carry a precise date. So how did researchers ever narrow this down to a specific night, let alone a specific hour? The answer was standing in the mud. Literally standing, dead, upright, bark still on some of them, rooted in tidal flats along the Washington coast where nothing should be able to grow. Ghost forests. Stands of red cedar killed not by fire, not by drought, not by beetles working slowly through the cambium over decades. They drowned. The land beneath them dropped, suddenly enough that salt water moved in before the trees could respond, before they could even fall. And that detail matters more than it sounds. A gradual subsidence would have stressed the trees over years, produced visible ring narrowing, allowed some to die early and some late. These didn't show that. They stood together, killed together, the tidal mud preserving them in place like something pressed between pages. Brian Atwater, a USGS geologist working the Washington coast in the 1980s, began coring those trunks and counting rings. The outermost rings, the last ones the trees ever laid down, dated to sometime in the late 1600s. That narrowed the window. But tree rings record growing seasons, not calendar dates. They could say, this tree's last summer was 1699. They could not say, this tree died on a Tuesday in January. To lock in the precise night, researchers would need something the trees couldn't give them, which is exactly where the Japanese archives come in. Gordon Jacoby had spent decades reading trees the way other scientists read instruments. A dendrochronologist at Columbia's Lamont Doherty Earth Observatory, he understood that a ring isn't just a year, it's a biography of that year. A wet summer, a dry one, a frost that came too early. The outermost ring is the last sentence the tree ever wrote, and Jacoby was trained to read the punctuation. When he examined the ghost forest cedars alongside Atwater's coring data, the outermost complete rings pointed consistently to 1699. The trees had survived that growing season, but here is the detail that tightened everything. The final ring on several specimens wasn't complete. It had started forming. The cells were there, early wood laid down, and then it stopped. Abruptly, the tree didn't finish its last year. It was killed mid-season, after the summer growth had begun but before the ring could close in autumn. That partial ring is a timestamp. It says the trees were alive in the summer of 1699 and dead before the spring of 1700. 6 months, maybe 8. The ghost forests weren't just evidence of sudden subsidence. They were a clock, still running, stopped at a specific moment. The question now was whether anyone could read the hour. The clock had stopped somewhere between summer 1699 and spring 1700. But a stopped clock only tells you when. It doesn't tell you what, or how far the disturbance had reached. For that, researchers needed a witness, and one existed on the other side of the Pacific, in a language nobody on the Washington coast had ever spoken. Kenji Satake, a geophysicist with a historian's patience, began working through Japanese archives in the early 1990s alongside a small group of colleagues. They weren't looking for earthquake records. They were looking for the opposite: tsunami reports that arrived without any preceding shaking. An orphan wave, a wave that had crossed an ocean and lost its parent. What they found, buried in regional documents and domain logs, were 4 separate accounts describing unusual flooding along the Sanriku coast and other stretches of Japan's Pacific-facing shoreline on January 27th and 28th of 1700. The accounts described water rising without warning, in the dead of winter, at night. No trembling, no roar from the earth, just the sea, arriving uninvited. One record went further than the others. A samurai estate had documented the exact height water reached on one of its buildings. A mark on a wall, essentially, translated into a measurable wave amplitude. That single detail meant researchers could now work backward. Given the wave height in Japan, could they calculate where the earthquake had originated, and how large it must have been? That question would take years to answer. But one thing was now settled. The date was January 27th to 28th, 1700. The clock Jacoby had stopped in the cedars finally had an hour. The date was fixed. Now the work was to find the address. Satake and his colleagues had 4 Japanese accounts and 1 measurable wave height, a watermark on a wall essentially, preserved in a samurai estate record. That single amplitude became the key input for a reverse calculation. Feed the wave height into a tsunami propagation model, run the clock backward across the Pacific, and find the source. The physics of tsunami travel is well understood. The ocean is not uniform. It has depths and ridges that bend and slow a wave. But those variables are mappable, and once mapped, a wave's travel time becomes a precise function of distance and bathymetry. Satake's team built models of every plausible source zone along the eastern Pacific Rim and asked a simple question: which one produces a wave that arrives at the Sanriku coast at the right time, at the right height? Every model pointed to the same stretch of seafloor, the Cascadia subduction zone, the fault running off the coasts of Washington and Oregon. The orphan finally had a parent, but matching the source zone to the location was only the first half of the answer. The amplitude recorded in Japan required something more alarming: a rupture length of roughly 1,000 kilometers. That wasn't a partial break. That was the entire margin going at once, a scale of earthquake Cascadia had never, in modern memory, been credited with. And if it had done it in 1700, the question that followed was unavoidable. Had it done this before? And could it do it again? 1,000 kilometers of fault rupturing at once. That number didn't just answer a historical question, it detonated an assumption that had held for decades. Because the geologists who had mapped the Cascadia subduction zone since the 1960s had looked at it and largely concluded it was quiet for a reason. The fault appeared well coupled, yes, but the thinking went that coupling without stress release meant slow, aseismic creep. The two plates grinding past each other too gently to build the catastrophic strain a great earthquake requires. Cascadia, in the prevailing view, was a locked fault that didn't really rupture. It just slid. The 1700 evidence said otherwise, and it said so with a specificity that was hard to argue away. A wave that height, arriving at that time, required a rupture that was not partial, not segmented, but full margin. Then someone asked the structural question. Cascadia's geometry, the angle of subduction, the age of the descending plate, the temperature profile, matched almost exactly the fault system that had produced the largest earthquake ever measured anywhere on Earth. The 1960 Chilean earthquake, magnitude 9.5. Two faults, nearly identical architecture. One had gone catastrophic within living memory. The other, it now appeared, had done the same thing in 1700. Cascadia wasn't a quiet fault, it was a sleeping one. And that raised the question nobody in the region was ready for. How often does it wake up? To answer that, geologists needed more than 1700. One event is a data point. A pattern is a warning, so they went looking in the one archive that predates every written record and every living witness: the ground itself. Cores drilled from coastal marshes along Washington and Oregon pull up something distinctive when Cascadia ruptures. The shaking drops the land surface abruptly, sometimes by a meter or more, and the tsunami that follows washes a sheet of marine sand inland over what had just been a freshwater marsh. That sand doesn't belong there. It's coarser than the surrounding peat. It contains marine microfossils, and it has a sharp lower boundary, the exact moment the wave arrived. Then peat slowly accumulates on top again, and life resumes, until the next rupture buries it again under another sand sheet. Core after core, the same stratigraphy repeats. Layer of peat, sheet of sand, layer of peat, sheet of sand. Each buried sand layer is a separate earthquake, a separate tsunami, a separate catastrophe. Offshore sediment cores pulled from the seafloor add turbidites, submarine landslide deposits triggered by violent shaking that extend the record even further back. The count assembled across dozens of sites reached at least 19 full or partial Cascadia ruptures in the last 10,000 years. Average recurrence, somewhere between 200 and 500 years. The last rupture was 325 years ago. That number sits at the edge of the window. And the cities that didn't exist in 1700, Seattle, Portland, Vancouver, sit directly above the fault. 19 ruptures in 10,000 years. And the last one left a trail across 3 entirely separate records that had no knowledge of each other, and yet landed on the same night. The coastal tribes of the Pacific Northwest carried the memory in oral tradition. A night without warning, the ground convulsing, the sea rising and taking entire villages. The accounts described not myth, but aftermath. Specific losses, specific places, the particular quality of a wave that didn't behave like any storm surge. Researchers who finally listened carefully found that the traditions pointed consistently toward the end of the 17th century. The dead cedars standing in Washington's tidal flats gave a different kind of testimony. The outermost growth ring in those trees, the last season they were alive, dated to 1699. The flood that drowned them came after that growing season ended, and before the next one could begin. That narrows it to a window between August of 1699 and May of 1700. The Japanese archives closed the window. A tsunami struck the Sanriku coast and the shores of Hokkaido on January 27, 1700, local time. No earthquake preceded it. It had crossed the open Pacific from a source far away. Working backwards from the wave's travel time, researchers calculated when it must have left the Cascadia subduction zone, sometime between 9 in the evening and midnight Pacific time, on January 26th. 3 lines of evidence, 3 continents away from each other, in method and in culture, all pointing to the same rupture, the same night. What the oral traditions remembered, the trees confirmed, and the Japanese archives dated. The question that remains is what that night actually felt like to the people who were standing on the shore when the sea went out. The people standing on that shore had no category for what was coming. The ground moved first, not the rolling sway of a distant tremor, but a deep, violent shuddering that knocked people from their feet and brought longhouses down. The shaking lasted minutes. Accounts from nations along the coast described the earth behaving as though it had become liquid, the ground heaving and settling into new positions it would hold for centuries. Some areas along the Washington and Oregon coast dropped by as much as 2 meters in those minutes, permanently. Cedar forests that had stood on dry ground found themselves suddenly at tidal level, their roots drowning in salt water, their trunks beginning the long process of petrification that would preserve them into the 21st century. Then the sea went out. Not an ordinary low tide, a withdrawal so complete and so fast that the seafloor lay exposed, strange and alien in the darkness. The oral traditions describe people walking out onto ground that had never been walked on. And then the horizon changed. The wave that had been building across the Pacific for hours arrived at a coast already subsided, already weakened, already lowered to meet it. Survivors ran for high ground. Entire villages, the longhouses, the canoes, the winter stores, went under. The accounts described people watching from hillsides as everything below them disappeared. That instinct to run uphill, to keep running, is precisely what tsunami preparedness educators teach today. The oral traditions were not recording a myth, they were recording a survival protocol that worked. And here is where the story shifts from geological detective work to something harder to quantify. Those oral traditions didn't just preserve a memory of the disaster. Several of them embedded instructions inside the account. Where to move, which hillsides held, what the water's retreat meant, how fast to run and in which direction. The knowledge wasn't stored as raw description. It was stored as procedure, refined across generations that had almost certainly witnessed prior events on the same fault. The 1700 rupture wasn't the first. Cascadia had broken before. And the people living on its coast knew that, not in the abstract, but in their bones. Encoded in the stories children were taught, in the protocols that became reflex. For a long time, academic geology treated those stories as legend to be decoded rather than evidence to be weighed. The breakthrough here wasn't just matching a date, it was the recognition that a community living continuously on a coastline for centuries, across multiple catastrophic events, would develop an observational record that no single scientist's career could replicate. Precision isn't always written in numbers. Sometimes it's written in the instruction to run uphill and keep running. That reframing has consequences far beyond this fault, far beyond this coast. If oral traditions can encode stratigraphy, tsunami dynamics, and survival protocol with enough fidelity to be verified by tree rings and Japanese archives, what else are we not reading carefully enough? What else are we not reading carefully enough? That question hangs over everything that comes next, because the fault those oral traditions described isn't a historical artifact. It's still there. The same subduction zone that ruptured on the night of January 26, 1700, runs for roughly 700 miles beneath the seafloor off the coasts of Northern California, Oregon, Washington, and British Columbia. Seattle, Portland, and Vancouver sit within its reach. Not metaphorically, structurally. The sediment record shows that Cascadia has produced full-margin ruptures, the kind that move the entire locked plate boundary at once, roughly every 200 to 500 years, with some clustering closer to 200 to 300. The last one was 1700. That was 325 years ago. The recurrence window is not comfortably far off. By the interval record, the Pacific Northwest is deep into the range where another event becomes due, not distant. Emergency planners don't soften this. They refer to the anticipated next full Cascadia rupture as the really big one, a sustained magnitude 9 or greater, lasting 4 to 6 minutes of violent shaking, followed by a tsunami reaching coastal communities in as little as 15 to 30 minutes. Most of the infrastructure in the region, bridges, hospitals, water systems, older buildings, was not designed for that. So the 1700 event is not finished history. It is the last data point in a series that is still running. The question of what it means, as warning, as legacy, as a test of how knowledge survives across centuries, that answer still has to be written. The answer was always there, not in one place, in three, separated by an ocean and by centuries of people who never compared notes. Coastal tribal nations passed it down through every generation because forgetting would have been fatal. Japanese officials wrote it in harbor ledgers because that was their job. Trees recorded it in the width of a single ring because chemistry doesn't editorialize. What took so long wasn't the absence of evidence, it was the assumption that evidence only counts when it looks like the kind we already know how to read. Here is the thing that should stop you cold. The oral traditions were right about every physical detail science later confirmed. The shaking, the withdrawal of the sea before the wave, the height of the water, the villages lost, the approximate time of night. Every single one. Which means they were not legend, they were journalism. Careful, accurate, deliberately preserved journalism, passed through human voices for nearly 300 years because the people who survived understood that their descendants would need to know. And that opens a harder question, the one this story leaves unfinished. How many other catastrophes are hiding inside oral traditions we haven't yet learned to read? How many warnings are already spoken, already remembered, waiting for the rest of us to finally listen? One night in January 1700, the ocean came in. For centuries, no one outside those communities knew when, or how large, or how far the damage reached. Then three sources that never knew about each other. A story told by survivors, a ledger kept by strangers across the Pacific, and the last growth ring of a drowned tree pointed to the same night. The orphan wave found its earthquake, the earthquake found its date, and a moment that had no witnesses history recognized turned out to have been witnessed by everyone it touched, and remembered exactly as it happened.